All right, everybody, welcome back. So this is our last day on climate change. Hopefully you guys are prepared for your exam tomorrow. Just a reminder, that's going to be on tsunamis, volcanoes, and rivers and flooding. It's going to be held here in person. No Scantron, just circling stuff on the exam packet. I should have your grades done over the weekend, and then I'll get them back to you on Monday. I'll bring those into class on Monday. If you're not here and you still want it, and you're usually in class on Zoom, you can come to my office and pick it up if you want it back. Yesterday we were talking about climate change throughout Earth's history. And we had a couple of big takeaways specifically from that. So obviously, plate tectonics is going to influence our climate on Earth. Plate tectonics is one of the long-term factors in climate change because the climate changes constantly throughout history. It's always going through these long-term fluctuations. We also have the silicate carbonate cycle. So we have carbon dioxide coming out of our volcanic vents. All those holes on the Earth's crust that are just spewing out ash and lava are also spewing out carbon dioxide, as well as increasing the amount of silicates on the Earth. And these things happen in balance in natural systems. So the Earth is always trying to find a balance in its climate throughout these times. So currently we're in an ice age or a glacial period. So the Pleistocene, 2.6 million years ago, we have these advancing ice sheets covering most of the Earth, most of the northern hemisphere especially, where these ice sheets cover like all of Canada and most of the northern parts of the United States, Maine all the way down into like northern Pennsylvania. So we're currently in an interglacial period that started around 12,000 years ago, where we get less glacial ice, more temperate climate overall, more warmer temperatures, more precipitation. And we also talked about other things that influence the changing climate that are outside of our control, like Milankovitch cycles, the obliquity, precession, and eccentricity of the Earth's orbit and its tilt on its axis. So this is going to influence climate based on how much solar radiation is getting reflected versus absorbed by the Earth itself. So that's the natural stuff that happens during climate change. But to understand if we are having an effect on our climate today, we need to understand the climates of the past. And how do we know that? Obviously, we weren't there, we weren't recording stuff. So how do we know about the past climate? So we have three different ways of gathering data. So we have the instrumental record, the historical record, and the paleoproxy record. And we're going to go through each of these real quick. So the instrumental record obviously means we have scientific instruments actually measuring stuff. So whenever we have that, we're able to get an actual data point from whatever period of time that we have the instrumentation for it. So we've been measuring temperature on a daily frequency since 1860. Those global temperatures have been recorded throughout human history since 1860. So we have just tons and tons of temperature data collected on the ground. And since then, we've gotten a lot more advanced with collecting temperature data so that we can get even more accurate temperature data ranging all around the world at every point on Earth, which is pretty sweet. So let's make sure we can look at a graph. How much has global temperature changed since 1880, roughly? You have the answer? Just shout it out. About 1.2? That looks about right. So we have our low of around 0.45, high around 0.75. Yep, around 1.2 degrees Celsius. That's how much change has happened since 1880. Doesn't sound like a lot, but remember, this is the global average temperature. Specifically, the anomaly from our zero value. Remember that reference scale that we set up between 1950 and 1980, where temperatures are pretty stable. Okay. We also have the historical record. People have been writing stuff down for a long time, around 4,000 years. So if we have books and newspapers dating back for long periods of time, they record maybe not the exact temperature because they didn't have the technology to record that, but we can record other stuff. Like people will note the weather patterns. Diaries and journals will record whether or not it rained and how much. And we can also infer some specific observations like just from higher grain prices. And this can date back even to like the Sumerians, where they were using clay tablets. They recorded grain prices on those clay tablets. So we can assess what the climate was like based on if grain was scarce. If you had a bad growing season, that's most likely due to climate factors. They didn't have many other factors influencing that. Because of that, we also have to take into account anything else that would affect these types of direct observations and inferred observations. So like if we notice a spike in potato prices in Ireland in 1850, it wasn't very cold in Ireland at that point. We weren't going through this climate change stuff in 1850. That was just the potato famine. So we have to keep into account other historical factors that could impact those, like grain prices and things like that. And we can also use proxies. So by definition, a proxy is a stand-in, meaning it has the authority to represent something or someone else. So a lot of like board members on corporate boards will send a proxy because they don't feel like going to the board meeting. So they'll send somebody to represent them and represent their opinions and thoughts. So we have no thermometers here, no instruments, no direct measurements, but instead you're measuring different changes of other things that are indicative of a change in climate or temperature. And we have a lot of different ways to measure these. So we have vegetation proxies. So you've probably seen tree coring or lichenometry. We can look at the rock record, glaciers. We can look at different sediments that have formed, whether or not the environment was cold or hot. Obviously, we still have these huge ice sheets on the Earth's surface. They're shrinking relatively fast, but we still have them on the surface and we can still get data from these. And of course, the greatest sink in the entire world is seafloor deposits, because once it's on the seafloor, it stays there for a long, long time. So we're not going to really disturb anything. So that's going to trap a lot of data for us. So let's look at dendrochronology. Some of our students are in our grad department are looking at this right now. They're doing some short-term dendrochronology on tree roots along stream channels, which is a pretty cool project to look at. It's a lot of digging, but it's a pretty cool project. So trees grow in response to what climate they're in. So if you have a good growing season, you're going to have a thick growth ring. If you have a not good growing season, like it's drier, it's chillier, it's colder, you're gonna have a slow growing season. So that growth ring is thin. We all know that trees grow in rings, and if you core into that, you can count each ring, and that each ring is a year in that tree's life. So this is one of the best records that we have. Some trees are as old as 10,000 years. So that's a really, really long time and a really long data range that we can get all of this data from. The problem is it's a lot of trees that are this large and this old are in protected areas. So it takes a long time to get funding and permission to core these trees, and it's very difficult to do it safely. So that's why we do it from the root system, because the root system will always grow back, rather than if we just drill a hole into a tree, we may be exposing it to like certain fungus and diseases that kill trees specifically. But we can learn a lot about different climates on a yearly basis, annual basis, through tree rings. Do this a lot frequently. You can also use other biologic proxies. Pollen. Pollen is everywhere. It's this last pollen season was pretty bad. But all that pollen, it doesn't just dissipate and disappear. It ends up somewhere. It works like sediment. So it's carried by wind, falls onto the ground somewhere, and then it gets buried for long periods of time. So based on how these pieces of pollen are assembled and put together, we can learn a lot about past climates as well. Also, we can use some radiometric dating and learn a lot about sunspot activity through carbon-14 for our half-life dating. And same as trees, coral grows in a similar manner, grows in rings. This is carbonic calcite, CaCO3, calcium carbonate. So they can trap metals in these structures. Anything that's floating around in the ocean water, it can trap in those layers. Another ocean-borne thing we can get data from, sediment cores. So as that sediment accumulates, it always accumulates in layers. Remember the law of original horizontality. They're always depositing in these horizontal layers. And if we just drill into these and then make a core and pick it up, we can see each of these layers and learn a lot about the Earth. There's a lot of different chemical signatures that we can learn from sediment cores, and a lot of the people in our department have been on a lot of these research vessels, collecting sediment cores, throwing out buoys for monitoring long-term climate impacts. So a lot of people in the department are very familiar with this kind of thing. If you're more interested in these kind of research expeditions. So what are we actually measuring when we get that sediment core? We're looking at water specifically, and even though we have that ocean water circulating above it, that sediment is trapping relic water, specifically the gases in that water. So we have H2O as a liquid, H2O as a gas. We're specifically going to target that oxygen molecule in each of these sediment cores. So most of Earth's water contains that isotope of oxygen 16, and then a very, very small portion of it contains oxygen 18. The reason for this is obviously because we have oxygen 16, it has less atomic weight, so it's much lighter. It's going to be preferentially evaporated and brought up into the atmosphere. So during warmer times, warmer temperatures, we're getting more melt from glaciers, we're getting more water flowing into the oceans. All of that is going to be rich in oxygen 18. If we have colder temperatures, a lot of that water is going to be locked up in the glacier. It's not flowing into the water. It's not evaporating up into the atmosphere to rain down. So we're going to start getting enriched in oxygen 18. And this is what that looks like. So non-glacial periods, we have very light oxygen 16 coming into the ocean as runoff, coming into the ocean as precipitation directly, evaporating into the stratosphere, and all of that is going to fall in within the sediments that deposit on the sea floor. And during glacial periods, all that isotopically light oxygen is going to deposit on the glaciers. We're going to lock up a lot of that, so we get a much bigger concentration of that oxygen 18. So based on the difference in oxygen 18 and oxygen 16 that we see, we can tell a lot about the glacier. And that's what this data looks like. So based on its benthic value of oxygen 18, we can evaluate a rough temperature from each of these sediment cores. So this is 5.5 million years of data from this one sediment core that we've gotten from the bottom of the Atlantic Ocean. So we have so much so much information that we can get from this. And as we can see, we've had this gradual decrease overall from 5.5 million to today of global temperature. Now, as you can see, that variability is a lot lower back then. That's because we have, as you can imagine, 5.5 million years of sediment. It's going to accumulate a lot of weight. So we're trapping a lot more air particles. So that data is a lot better than what we're getting in shallower deposits, as you can imagine. So what we can take away from this, the climate was a lot warmer 3.5 to 5.5 million years ago. And that tracks because around 2.5 million years ago, that's the beginning of the Pleistocene. That's where we're getting that glacial period. That's where we're decreasing our temperatures. We're locking all that water up in ice sheets. So we're getting a much colder climate. So we can also get data from glaciers, what I study. So glaciers are born from snowpack. Snow reacts a lot like sediment, as sediment would when it turns into a sedimentary rock. The snow just falls as a blanket and it covers everything underneath it. As you pile on more and more snow, it's going to compact. We're going to increase the pressure. So as we increase pressure, we're going to change the crystal structure, and eventually it's going to pack down firmer and firmer until we get glacial ice. So we go from snow into ice just by sheer accumulation of snowpack. So these change over time based on temperature because glaciers grow and they shrink. So it's called a glacial advance and retreat, just because these are formed in high altitudes on mountaintops. So as they grow, they'll flow kind of, even though it's a solid, we describe it kind of like a plastic. It's a solid that kind of flows. But because it's so large and has so much weight behind it, it's going to plow through anything in its path. It's moving pretty slow, but it's still going to move things in its path. We're moving around 1 meter per day when we have glaciers. So we can also have a surging glacier, which is several meters per day, which we had a lot of a few years ago because they were melting really fast. So they were moving very, very fast. Most of that was from melt. So as these things are going to move down these hill slopes, they're going to carve out all the rock in front of it. And they leave these long U-shaped valleys whenever they retreat. So because they're so large and because they have so much mass behind them, they can transport huge, huge amounts of sediment. And wherever that sediment ends up, we can determine a lot about past climates and future climates. So glaciers leave their mark everywhere they are. So if you go into Central Park in New York, you can see all these exposed glacial rocks. These leave what's known as striations, which are just these scratch marks. If you were just to like scratch at the rock for a long period of time or drag something, it leaves all these scratch marks. In Glacial Grooves State Park, you can sit in these grooves like stadium seats kind of. That's how deep they are. So these things leave a really, really deep footprint wherever they go. We're also going to leave behind till. Till is just this hodgepodge of fine-grained sediment and huge boulders that glaciers kind of scour up and move. And these tills can they can leave glacial erratics like that big ass boulder over there on the left. So they can just pick up these boulders and drop them somewhere. So you'll see these random boulders in certain places. You can see them in Pennsylvania frequently. So they're pretty cool to see. But these deposits are found everywhere. And most of them are deposited as what's known as a moraine. So all a moraine is just a pile of glacial till. So glaciers advance along this U-shaped valley that they've formed. They're digging up all the sediment in front of it, and then it reaches its maximum advance point. So at that point, that's where it stops. It deposits all that sediment, it leaves it behind, and then the glacier is going to retreat. So all that sediment stays there, and that's basically a marker for where the glacier ended up. And we call that the terminal moraine, the largest advance that we've seen with a glacier. So over time, you see all of these smaller moraines behind the terminal moraine, because as the glaciers are advancing over time, they're not advancing as far. But we can also get all this outwash. As the glacier melts, all that water is going to flow over the land surface. Because we're in a steep gradient, we're not going to infiltrate. So we're going to flow over the land surface. We're going to mix in with all of that fine-grained sediment. So anytime you see like commercials for bottled water where they like are bottling it straight from a glacier and it's crystal clear, that is not what glacial water looks like. Glacial water looks like shit. It is just muddy, really muddy. All that fine-grained stuff down at the bottom mixes in with all that water. So you would not want to drink glacial water because you'd just be drinking something you could turn into cement. Yeah, so keep that in mind next time you go camping. Okay, so based on where glaciers were and where they are today, we can time their velocity and date their advance and retreat. So this is Muir Glacier in Glacier Bay National Park. It's a really huge ice field up north there. They still have a lot of glaciers, but they're not as huge as they were. So that photo was taken in 1941. These are taken at the same exact spot. So we have just this huge ice field covering this entire valley. And now it's all the way, it's really hard to see right in the back there. There's the glacier today. So based on glaciers, advance and retreat, we can also pull other types of data. So remember, if we get a lot of data from a bunch of different proxies, we're going to have a much stronger data set to work with. So if we just have one data set from a glacier versus a bunch, we're going to go with the more data, because that's going to help confirm some of the stuff that we're finding. So as the glacier is retreating, it's going to expose new rock surfaces, right? So lichens and some mosses will start to grow. And lichen, just like any other vegetation, absorbs solar radiation. And it stores that solar radiation. So based on the amount of radiation that we can see in these lichens, we can time how long ago that specific rock was exposed. So as you can imagine, if it's not going to go any further past that, because if there was a glacier on top of it, it's not going to get any sunlight because there's this huge ass glacier in its path. So this is another way that we can help date these glacial advances and retreats. And finally, we can get ice cores. So just like how glaciers form, ice sheets form the same way. Snow falls as a blanket, covers everything and traps stuff with it. So that includes dust, volcanic ash, wildfire ash, and pollutants, particulates, all the stuff that's in the air that we can't see. It traps all of that. Snowflakes are very intricate in their shape. So whenever it falls as a blanket of snow, it leaves a lot of air pockets. Just like with glaciers, as you increase that snowpack on top, it's going to compress and compress. And then you're going to leave a lot of air bubbles that are trapping the remnants of whatever the atmosphere was like when those air pockets were trapped. So you're getting a direct measurement of the atmosphere from that specific time. So these can trap all sorts of gases like methane, for example. We get a lot of these from the ice cores coming from Antarctica. So based on the amount of methane, that's proportional to the amount of CO2 that we get in the atmosphere. So we get all of these data points just from one core that we can see. And we can look back hundreds of thousands of years, which is pretty cool. We can also get direct CO2 measurements from this period. So this is taken from the Sea Dome, which is like a couple hundred kilometers away from the South Pole, right around there. So we're getting a huge amount of data. So let's make sure we can read this graph correctly. how far back does this climate record go? Just shout it out. 800,000. We can read. Great job, guys. Yeah, so that's a long period of time. In terms of geologic time, not so much, but we're getting a lot of info that that we can use from before human time. So, is this a proxy record for carbon dioxide? I accidentally gave you guys the answer, but in case you weren't watching, is it a proxy? No. Why? Because a proxy is a stand-in. So since we're measuring CO2 directly, this is not a proxy at all. This is a direct measurement from that period of time, which is super, super rare. You can't get that in any other field of study. You can't get that anywhere else. Like the only comparable thing is where you are looking into space and basically looking back into space-time. That's the only thing we can compare it to. Otherwise, if we didn't have any of this, we would be looking at proxy records. So like tree ring growth is a measure of climate. We're measuring the tree rings and we're inferring stuff based on the width of those tree rings. But because we're measuring the carbon dioxide directly, we're not using a proxy at all. But atmospheric CO2 is a proxy for temperature itself. So based on this graph, it's not a proxy record for carbon dioxide, but it is a proxy record for temperature because we can't measure the temperature from that specific time. But atmospheric CO2 is closely related to temperature. So if you're looking at this graph, what can we see? What patterns do we see? Yeah. Yeah, so these seem to be directly proportional to each other. They follow the same trend line, almost to a T, not exactly to a T. Most of the time, if you see things follow the exact same trend, that's usually pretty worrying. But it follows closely enough that it's very closely related, so we can relate the two. So we can assume that when CO2 levels go up, so does temperature, and vice versa. So in a natural system, we have this silicate and carbon cycle, where remember, silicates are the dominant mineral group on the Earth. Carbon is going to be one of the dominant gases that comes out of rocks. So we have these sources of CO2 from outgassing in the oceans, because the oceans are going to absorb a lot of stuff they're going to outgas from the surface. Also, of course, volcanic eruptions. We're just sending so much volatiles and gases up into the atmosphere. Eventually, just like with the water cycle, they're going to fall out of the stratosphere, enter into these what's known as sinks. They're going to be taken up into the ocean. They're going to be taken up into vegetation, biological uptake. So photosynthesis takes in CO2 and releases oxygen. As we're depositing stuff, we're going to eventually subduct them underneath tectonic plates and back into the mantle, where it's going to melt back down. And we can also weather those silicate minerals down. So that's what that chemical equation is at the bottom. It's the weathering of silicate. So if we have a normal natural system, no human engineering, no fossil fuels, this is what that looks like. We have rising and falling CO2 rates naturally over time. It is very hard to see on this graph, but the closest as you can get to the zero, that yellow line shoots up all the way up to the top, which whenever you look at it online after I post these, you'll be able to see it. But this is what that looks like. You have just in glacial periods, you have lower CO2. It's getting locked up in glaciers and ice sheets. Then as stuff melts and gets warmer, you're releasing CO2, creating more greenhouse gases and creating a stronger greenhouse effect. Okay, so we talked about Earth's energy budget and what determines it. Obviously, solar output, stuff that's coming out of the sun and towards Earth, and changes in Earth's rotation or orbit, those Milankovitch cycles. We can't control that one bit. So if we have increased sunspot activity, we're going to warm stuff up. So like before 1960, these solar cycles are agreeing with changes in temperature. After 1960, these are not matching at all. So right there is 1960, right after the label year. If you look up there, as we're approaching 1960, we're pretty much matching. We're rising and falling at the same rates with solar activity, but solar irradiance has been decreasing since 1960, but temperature has been rising. So what's going on there? What about our Milankovitch cycle? What does that look like? Well, we're not changing that much either. We're in a slight cooling Milankovitch cycle because we're extending our eccentricity. Remember, if we're getting periods of our orbit where we're closer to the sun and farther away from the sun, but a long period of time during our annual year and our annual orbit, we're much further away from the sun. So that's should give us more cooling. We also have our internal radiation. Remember, stuff that gets absorbed, all that solar radiation that gets absorbed can get reflected. Some of it gets reflected by ice sheets. Some of it gets absorbed by vegetation. Some of it gets trapped in our atmosphere. This is what we call the greenhouse effect. And this can be controlled by humans. So we talked about our permanent gases, how most of the atmosphere is made of nitrogen. Our variable gases can change constantly. So water vapor is a big one, CO2 is a big one, methane and nitrous oxides are also big ones. So they've always been in the atmosphere in small amounts, and they change based on climate conditions, but these tiny changes can reflect bigger climate change impacts. So greenhouse gases work much like regular greenhouse works. Whenever you think of a greenhouse, you think of those glass paneled structures, allowing solar radiation to come in, and then it traps most of that heat inside. So even though it's snowing outside, you can have tropical plants in your greenhouse. Greenhouse gases work similarly, and our atmosphere is allowing some of that radiation to come in. Our greenhouse gases are going to trap a lot of that radiance and keep it in our atmosphere. So if we look at, here we go. So if we look at oxygen and nitrous oxide is going to be bumped into that. This is the solar radiation spectrum. This is our incoming solar radiation in the rainbow. We're not absorbing any of this, really. But once we get down to CO2, we are going to absorb a lot of it. So does H2O. And as all of this stacks up until we get what looks like our atmosphere at the bottom here. Okay, so we've talked about this. 48% of the sun's energy is transmitted through. Most of it is reflected off. Of that gets transmitted through, 49% of that is absorbed by everything on the surface. And then 17% of this is emitted back by long wave radiation, infrared radiation. That's why as the sun falls onto the other side of the Earth at nighttime, all that radiation is going to come out of the Earth. So as we're re-emitting radiation back from the Earth's surface, those greenhouse gases are going to create a surface that can trap all of all of that radiation. So that radiation is going to basically be re-emitted back to the Earth's surface. So rather than escaping as it normally would, it's going to come back to the Earth's surface and warm up again. So in normal standard conditions, because we do create greenhouse gases naturally, we have the greenhouse effect is a good thing. It creates, it's the reason that life on Earth exists. So it would be a lot colder. We would be in what's known as a snowball Earth if we didn't have greenhouse gases or the greenhouse effect. The problem is a runaway greenhouse effect is going to be where we're running into our issues. If we can't get any heat out, then we're just creating just an ever roasting oven of our planet. Okay, so let's look at some of the effects of the greenhouse effect. Remember, we talked about positive forcings and negative forcings. This is a positive forcing. Positive forcing, we're adding heat to our planet. So as we're warming the surface of the Earth, it's releasing infrared radiation. Some of that gets out, some of it is absorbed and stays in. So we're increasing the amount of heat. If we're increasing the amount of heat, we're going to melt stuff faster. So if we have less ice, remember, ice is, because of its white color, it's very reflective, high albedo. We're reflecting a lot of that incoming solar radiation. If we melt that ice rapidly, we're going to decrease total area of reflection. So we're going to be absorbing more solar radiation. So by locking in more heat, we're melting stuff, and that's going to continue to bring in more heat. So we're in a positive feedback loop here. Same thing with forests and vegetation cover. So at high latitudes, we don't have a lot of trees. You can see the tree line on a map of the Earth. As we get closer to those permafrost areas, those ice sheet covered areas, trees can't really survive in that. So there's a lot more bare ground. So you have more albedo, but as we have tree loss at lower latitudes, think of the equator, the Amazon rainforest, they don't have a minimal albedo effect. There aren't any ice sheets in that area to reflect anything. So having more trees in that area will have a greater effect from CO2 because those trees obviously absorb CO2. We also have land use and land cover problems. So just by building things, you're creating what's known as a heat island. So urban areas and large population centers have this problem. Anytime you are in a city, it's always going to be hotter than if you're on the same latitude outside of the city. So as you increase the amount of reflective surfaces, like blacktop buildings, you're going to be increasing the amount of radiation that can be absorbed. Like roads are very dark in color, so they're absorbing a lot of heat. So that's, if you just have a high density of roads, high density of slate buildings, you're absorbing a lot of heat. That heat gets emitted over time, so you get this heat island effect around all these big population centers. So this is going to continue to grow because we're getting more and more urban areas on the Earth's surface. More cities are continuing to grow. Most people think that the entire I-95 corridor along the United States East Coast is just basically one big city interconnected. And this is going to continue as we grow and grow in population. So we have all of these components, all of these things that influence the climate in some way. How do we put it all together and how do we partition out what's a problem and what's not? So this is where we get into climate modeling. And we look at the actual solar energy locked in and solar energy that is either absorbed or emitted with each of these variables. So we have ice sheets and vegetation. So these increase reflectance. we're going to have a negative 3.5 watts per square meter of ice sheets and vegetation. That's in solar energy output. We have greenhouse gases, CO2, CH4, N2O. So carbon dioxide, methane, nitrous oxide. This is also going to change the temperature. And we have aerosols. Aerosols, remember, are those particles that float up in the atmosphere. They're going to reflect stuff as well. So we have a negative 0.5 watts per square meter of aerosols. Remember, these are really small particles. So to create a surface of a square meter of aerosols, it takes a lot of them. So keep that in mind. Okay, so if we have a regular forcings in the natural environment, something I forgot to mention, these are the natural stuff. This is the stuff if humanity was not on Earth at all. So if we had all this ice sheet, all the ice sheets and vegetation that would normally be there, all the natural greenhouse gases that are emitted from volcanic eruptions and from evapotranspiration from plants, and regular aerosols from like volcanic ash or wildfires. So this is what we would get over that period of time with that negative climate forcing of 6.6 watts per square meter. We're getting this long-term trend over the Pliocene and the Pleistocene in a downward direction. However, as we're approaching the Holocene, we have this huge ass spike right after the last ice age. So the thing that was concerning the most is that the rate at which CO2 was increasing was much lower than the modern rate. So natural CO2 increases at a geologic rate, very slow, long periods of time, and it enables stuff on the surface to adapt to that change. But in the modern time, we have a very, very rapid rise. So 22,000 years ago, we have very, very small changes. So we're going from 22,000 years ago at 180 parts per million. In, where are we? 10,000 years ago, we were at 270,000 parts per million. So that's 22,000, sorry, math is hard this morning for some reason. 12,000 years, we have a change of 0.014 parts per million per year. That's very small. Fast forward to 1960 to 2000, 2 parts per million per year. That is a huge, huge acceleration, huge. So that's the concerning part that most climatologists are talking about. We aren't concerned about if climate change happens all the time, as we discussed. It happens naturally. It happens over long periods of time. During those long periods of time, life on Earth has been able to adapt to those changes, and if it doesn't adapt to those changes, it goes extinct. This is a very rapid change. So what do we do with this information? Okay, so this is going to be a similar graph to those natural climate forcings that we saw. This is going to be impacts of the industrial age. Why did I not have a better picture of this? I thought I edited this morning. Give me 1 second. Oh, there it is. 1 second. I'm going to get you a better, clearer picture. All righty. Okay, this one's better. So this is what the Earth looks like now in the industrial age. So these are all of our climate forcings, just like we had before, except now we have it broken down into gases, aerosol particles, and our heat input from the sun. So anything below 0 is going to be a negative forcing. Anything above 0 is positive forcing. So we have CO2, 1.4 plus or minus 0.2 watts per cubic meter, not cubic meter, square meter. We have the combined greenhouse gases of nitrous oxide, CFCs, chlorofluorocarbons. You find them a lot in refrigerants, and methane. We have O3. Who knows what O3 is? Nobody? It's ozone. Ozone is that big layer that helps insulate the Earth in the stratosphere. We have black carbon, which is just another term for soot. That's the stuff that gets emitted from most coal power plants, just because it can't clean down all those particles after they're burned. So it's just another term for soot. In our negative forcings, we have reflective aerosols, all those that stuff in the air that's going to help reflect stuff and insulate. Forced cloud changes, which we'll discuss. Land color change, that's basically changes in land use. So based on if it's greener or if there's more urbanization, there's less ice cover, that kind of thing. Then we have the sun itself. So let's add up the difference of all of these. So let's do the positive forcings. Go ahead and add those up and tell me what you get. Just use the first number. Don't worry about the plus or minus. What was that? 4.2. Okay, so 4.2 in the positive forcing. How about in the negative forcing? What do we get? Negative 2.6. So 4.2 minus 2.6. What is that? What was that? 1.6. So we have a positive forcing of 1.6 constantly. So we're going to constantly get warmer with this system. I forgot I had that question there. Well done, guys. You didn't even need any guesses. Okay, and that's what this looks like over this entire period of time. So if we have a climate forcing of 1.6 watts per square meter, we're going to have a change overall over that entire period of time of 1.2 degrees Celsius, global annual average. So that's huge. So in order to understand that, we got to break down Earth's carbon budget. So everything on Earth releases and absorbs carbon. So we've done all these budgets before. We did a sediment budget for talking about littoral cells on the beach. We did a water budget for discharge, water coming in versus water coming out from precipitation, runoff, infiltration. We'll do the same thing with carbon. So we have oceans. Oceans release CO2, but they also take in a lot of CO2. Remember, oceans are like the biggest sink in the world. They're taking in pretty much everything. So in gigatons of carbon dioxide per year, oceans are releasing 332 gigatons, but they're also taking in 338. So we're taking in 6 gigatons more per year than they release. So that's good. Vegetation, they're releasing 439 gigatons, but they're taking in 450. 11 gigatons per year more that they're taking in. That's good. Fossil fuel burning and land use, we're just releasing. We have no way of capturing that from fossil fuel burning and land use changes. So all we're doing is adding to that problem. We're not taking anything out of it. So why do we produce atmospheric CO2? Because everything we use today relies on burning stuff. So the energy that's powering these lights in this projector, just the production of getting coffee beans into my cup from Costa Rica to here in Newark, Delaware, that's going to produce CO2. And that's been growing over time, constantly. So as you can imagine, it's going to grow in proportion to populations, human populations. So if we have, starting in 1850, we have a much lower population. much more dominant by forestry and timber. That changes in land use is really what's going to impact our global carbon output. Once we start industrializing, we're going to be using more fossil fuels. The advent of the steam engine really took that away. So as we're approaching 1900, we're industrializing more and more. Then 1950s catch up. We have the baby boom after World War II. So we're going to increase the population vastly. So we have an increased population. We have no more huge conflict. We're going to be using a lot more energy. So we have to up our energy production. So we're going to burn more fossil fuels. And that's continued on and on and on since 1850. That was not in here. Okay. So that was CO2. Let's talk about the other stuff. Specifically, let's talk about nitrous oxide. So nitrous oxide has also increased over the industrial age. So nitrous oxide is produced from volcanic action. So from our measured years, year 0, all the way up until the advent of the industrial age. We're going to vastly increase our nitrous oxide and our methane. As you can see, methane is actually starting to overtake CO2. Can anyone think why that is? It's another word for methane. It's not oil, it's close. It's natural gas. So coal is dying in America, and it's dying everywhere over the world, mainly because methane, while it's still a fossil fuel, it burns more efficiently. It's a lot cheaper to produce. And so it's become the primary fuel source for America, especially Russia as well, Canada. So a lot of Western countries are now powered by natural gas plants instead of coal-fired plants. So just in that time, we had a 20% increase in our nitrous oxide. So we talked about the nitrogen cycle a little bit. So natural cycles comes out a little bit in volcanoes, but also the breakdown of plants by bacteria. That's going to produce a lot of nitrogen. So you have nitrifying bacteria that come from decomposers. They form nitrates, and then you have denitrifying bacteria that break down nitrates. So once you break down nitrates, you get N2, atmospheric nitrogen. So that's going to really impact our nitrogen production. But most of our modern nitrogen comes from fertilizers. So we live in a huge country with a huge population. We have a whole mess of farms producing food for the entire population of the United States. They use a lot of fertilizer. As you can imagine, it's really hard to grow things naturally whenever you have to produce food by the gigaton each year. And you have these massive, massive industrialized farms. So you have to use a lot of fertilizer in order to grow stuff properly. So most of it comes from fertilizer, also rocket fuel, and high performance cars emit a lot of nitrogen just based on the fuel content that they have to use. If you produce nylons, you're going to produce nitrogen oxide. And of course, by burning fossil fuels, that is also one of the emitters. So nitrous oxide comes from your car as well, if your car is gas powered. So nitrogen is really important to study because it depletes the ozone more than anything else. So we'll have a hole in the ozone that's going to impact solar radiation. So we'll get more heat, and those greenhouse gases are going to lock that heat in. So the ozone layer is super important because it helps to insulate us. If we didn't have an ozone layer, we would, number one, get sunburned all the time. Number two, die from cancer probably at the age of 15 constantly. So that would be the human lifespan if we did not have an ozone layer. All right, so let's talk about methane. So obviously we've increased this the most. So the main sources of methane, we talked about industrialized agriculture. That includes meat production. So America is a big fan of meat, specifically beef. I know I am. I'm sure some of you are as well. That produces a lot of methane, literally from cows farting. If you have a large enough population of cows and you're feeding it stuff to make it fatter, so you can get bigger, larger, fattier cuts of meat, you're going to produce a lot of methane from each cow. And that amount of methane can be measured. It's measured in such a large amount that it's become a problem. There are a number of ways to mitigate that, and we can talk about that at the end of the class. Also, decomposition is going to build up methane just by the breaking down of organisms, breaking down stuff like trash from landfills. That creates sources of methane. But we've also figured out how to tap into that to use that methane, which is good because you don't want methane just leaking into the atmosphere. You want to at least use it first. It's bad because it's still going to create some emissions. So by capping, landfills have become very good at capping themselves and then creating wells that trap all of that rising methane. And then that gets funneled into a power plant that you can use it. Also cultivating rice paddies produce methane. The nutrient transfer from the rice plant with the soil itself creates a lot of methane. As you can imagine, a lot of areas in Southeast Asia and China, they have huge, vast rice paddies because rice is a very staple part of the diet there. So these are huge contributors to CH4, not as large as other sources like industrial agriculture. Also, and this is a problem with the natural gas industry, once you're done with a well, that just means you can get all that you can out of it. There's still stuff down there, but we just can't extract it anymore. So what they're supposed to do is they're supposed to abandon that well and cap it. Sometimes it's not capped properly because the goal of a natural gas production company is to, you're done with this one, move on to the next one as quickly as possible because you're only making money if you're producing gas, right? So if you don't do it properly and you do it shoddily, you're going to leak that natural gas constantly. If you're leaking natural gas, number one, natural methane, contrary to popular belief, it's odorless. You cannot see it. You cannot smell it. That rotten egg smell that you get whenever you like open a propane tank or something like that, that's added after it's been processed. That process is known as pickling. One of my cousins actually does that. He works for a gas company out in Ohio. So his title is actually pickler, which has always been a real good source of jokes for me. But yeah, so they add that smell just because just by smelling it, you can tell if there's a gas leak. That's been helpful in the beginnings of the natural gas industry, just to tell if there was a leak and you had a hazardous situation. But because we can't see it, we can't smell it in its natural state, we can't detect it unless we're using like infrared cameras. You can see them on infrared cameras easily. So leaky gas lines are a huge source of pollution from methane. Okay, black carbon, this is going to be soot. So this is from fossil or biofuel combustion. This is going to be your lump fossil fuels, your coal, ranging all the way from peat moss to anthracite. So on your coal scale, you have coal is formed mainly from peat that gets buried and goes under more pressure and pressure and pressure. It's almost pure carbon. So it burns really a lot more efficiently than say wood. But you have your range goes from peat to lignite coal, which is really dirty. It's not a high grade coal. Most of Germany's coal production is lignite. They have a lot of lignite there. They don't have anything like we do in the East Coast, Pennsylvania. We have anthracite, which is the highest grade. It's pretty shiny. Actually, whenever you grip it with your hands, it doesn't leave much film. because it's so compressed. But if you touch lignite and stuff, you're coming away looking like a coal miner. So these sources, obviously, we've been powered by coal for a long time, but that is starting to decline in America. Most of the emissions in the US and Europe are under control because we have something called coal scrubbers. It's just this way of managing the outflow of that coal. So you don't get all this black smoke coming out of these smokestacks in America. You mostly get a more white color. So not only is that, it's still bad because it's carbon that's still coming out. It's still carbon, but it's a little more reflective. So if you think of aerosols, it's more reflective. It's going to help insulate a little more than black coal. Also, if black coal and soot covers like ice sheets as it spreads over the earth, you're creating the threat of more melting. So keep that in mind. Big problem with this is that while the emissions are under control in the US and Europe, China and India have a lot less regulations when it comes to coal production. Most of the regulations when it comes to other forms of energy usage are a little more regulated in those countries, but for some reason coal is not. So China actually surpassed the United States as the largest annual producer of CO2 in the annually. So that is a mantle that we as the United States should be happy to pass on. We still have a long way to go, but keep in mind that all the emissions in the world are going to affect us as well. So as cheesy as it sounds, we're all in this together. However, although China is producing more CO2 than us per year, from 1959, we have produced more total. So that regression of fossil fuel use in America started around 2005. We started developing a lot more renewable energy. The 2008 financial crisis really helped as well because less people were spending money, so less consumption, less production of products, less energy usage overall. So it's really sad that economics and the environment have not been on the same path in that way, and there are a lot of they're usually disproportionately related. But that progress on that renewable energy has been slowing. Its peak was in 2017, and ever since then we kind of plateaued in our renewable energy production. So hopefully we can get that back up. All right, so let's talk about some of these reflective and insulative processes. Forced cloud changes, what does that mean? Well, as you can imagine, people fly a lot around the world. Ever since the advent of the airplane, we've flown everywhere and more frequently. More people have traveled by air than most other forms of international travel. It's the easiest way to travel to other countries. So we have a huge impact on the atmosphere from that. So this is Würzburg in 2010. No air traffic versus lots of air traffic. So you're creating more clouds just from those jet engines. So if you have more cloud cover, that works as an albedo. You're reflecting stuff. All that is water vapor in the sky. That's going to help reflect a lot of that incoming solar radiation. So there are some people that are experimenting with cloud cover and seeing if that would be useful as a way to combat and mitigate climate change. It would take a lot more than just clouds like this, I can tell you. So, and the emissions that would be caused by running that many planes constantly would probably make it worse than better. So keep that in mind. Okay, so if we're comparing natural systems to anthropogenic systems, how much of that can be attributed to natural processes in terms of the temperature anomaly? How much of it is due to human influence? So the best way we can look at this is we have observed warming, our greenhouse gases, our other anthropogenic forcings, our combined anthropogenic forcings, and the effects of our natural forcings. So if you look on this graph, there is a block at natural forcings. It's very small, but it's there. So most of this is obviously coming from anthropogenic sources. So the natural stuff, think of the natural forcings that would impact this. We have volcanoes, we have, yeah, that's pretty much it. So are you going to stop a volcanic eruption anytime soon? No, you're not. And if you had the technology to do that, you'd have the technology to stop any of these other problems first. So blaming nature for greenhouse gas emissions and CO2 in the atmosphere is not going to get you anywhere in terms of fixing the climate change crisis. All right, so the key takeaways on climate change. Number one, greenhouse gases create the greenhouse gas effect. They trap that radiation rather than that long wave radiation going out to space. It bounces back. On long time scales, we have carbon dioxide fluctuating in the Earth's atmosphere based on volcanic activity. So it happens on much longer time periods and much more gradually. So Earth has been warmer than it is today. It's also been a lot colder. We've had higher CO2 levels in the past, but the rate at which we're accumulating it is very worrisome. And it's Earth is able to adapt to long-term changes rather than short-term rapid changes. And we are like that as well. And of course, the observed warming trend that we see is matching anthropogenic forcings, not natural climate forcings. So that rate increase that we see comes around the Industrial Revolution. So it is undeniable in that fact. So I don't have anything else left for this today, but I would like to discuss what you guys think about mitigation, because something I didn't mention here is hazards. I think it's really important to understand how climate change works and how complex and interconnected everything is before we talk about hazards. What do you guys think the hazards are from climate change? What do you think the big ones are? Doesn't even have to be the big one. Yeah. Rising sea levels is a great one. So we talked about tsunamis and flooding in this class. Higher the sea level you have, that's going to impact how devastating, say, a tsunami is, or the next flood. If you have a higher sea level, you're going to have, it's going to go over any geoengineering that you build to protect your town or coastal city against a tsunami. And obviously, once you build a seawall, it's really hard to just add a couple of bricks to it and think that's going to be strong enough to stop a tsunami. What are some other things that you think of? And you guys in the Zoom chat can type stuff in as well. It doesn't even have to be a flashy hazard that we've talked about in class. It can be anything. Tropical storms, yeah. So we have hurricanes on the East Coast frequently. And as we saw when we talked about flooding, they're becoming more and more frequent, as well as growing in their strength and magnitude. So as you can imagine, more hurricanes, stronger hurricanes is going to create a lot of problems. It's not just going to cause a lot of death and destruction, but we also have to repair that stuff every year. So that's another thing you have to worry about. So really, it's going to affect your wallets first, because where does that money to repair stuff come from? It comes from you. That's your tax revenue. That's your tax money. So, ooh, Adele, very good. Yeah, something I forgot to mention: coral bleaching. This is when, as you have more CO2 in the atmosphere, that stuff gets rained out. Whenever you have combined H2O with CO2, and we can do that chemical equation, that's H2CO3, otherwise known as carbonic acid. So that carbonic acid is really good, Marley. Yeah, ocean acidification. So overall, we're going to acidify the oceans if we increase the amount of carbonic acid. It's specifically also going to bleach these corals because these corals are made of calcite, calcium carbonate, CaCO3. So that carbonic acid is going to break down that calcite, and you're left with just a dead coral reef. Coral reefs are really important because they're biodiversity hotspots. They're really important in the ecosystem. So if you just kill a whole coral reef, you're going to kill a lot of other aquatic species. So we're lowering our biodiversity by acidifying the ocean as a whole. Acidifying the ocean is also going to change spawning for certain fish, because some of them swim to fresh water and some of them swim to salt water to spawn. So if you change the pH of where they spawn, they're going to have some of their, more of their eggs may not survive. So you're going to have a lower population of whatever species that is. What else? Let's talk about humans. I like these, but let's talk about humans. Because whenever climatologists talk about climate change, what they're really concerned about is human life on Earth and how it's going to affect human civilization. What if we have warmer temperatures, what is that going to affect? What are we going to need more of? Water. Very good. More fresh water. And do we have a lot of fresh water on Earth? No, we don't. So if we have drier periods of time, warmer periods of time, we're going to have a lot more droughts. And believe it or not, most plants in agriculture require water in order to grow. So if we have less water, that means less water coming from the sky, that means we're going to have to pump more water from our groundwater aquifers. Like the Ogallala Aquifer in central Oklahoma. It goes from Oklahoma and Texas all the way up north. Used to be one of the biggest aquifers in America. Huge, like billions of cubic feet of water in that aquifer. It is very low now. So we've really used a lot of that water sources. And then if you can't grow stuff in certain areas, certain poor countries that don't have that access to groundwater or the funds to drill wells to access groundwater, what's going to happen to those farmers? They're going to move somewhere else. So then you have political and social and cultural problems just by people from moving from where they used to live to new places. You're going to have denser populations and then whole other myriad of problems that you can have from that. So we're not going to discuss any of the politics of this in this class. We're just talking about the science. If you want to talk about the politics, come to office hours. I'm sure we could have a great discussion about it. But this is what climatologists have forecasted. These are the problems that are going to occur from it. And we haven't even listed them all. So it's really important to keep this in mind. I know a lot of you are not science majors, and that's great. I hope that you don't have a bad taste in your mouth from taking this course. I want you to walk away from this course having an appreciation for the science and hopefully incorporating these concerns and these thought processes into whatever your designated career path is going to be. So that's really the goal of geologic hazards. So I think that's it I have today. Does anybody have any questions? We have plenty of time if people want to go over just some review for the exam. If you have any lingering questions on exam 2. Do I have a list of things that are going to be over the exam? I do not have it with me. Let's see. So we have tsunamis, volcanoes, and rivers and flooding. Okay, so tsunamis. I would know. I would know how to calculate a velocity of a tsunami if you're given a time range and a distance. What is a velocity measured in? What are the units? That's a question for you guys. What are the units of a velocity? Meters per second, so a distance per time. So keep that in mind whenever you're calculating velocity of a tsunami. What causes a tsunami? It isn't just the earthquake, but it's the displacement of water. So keep in mind, displacement of water is what causes a tsunami, and what we get with deeper water and shallower water, and how they transmit, the directional component. I would know a lot of the vocab. All the vocab you need is in your lecture slides. Keep that in mind. For volcanoes, I would definitely nail down the different types of magma and their characteristics. Characteristics being, do we have a lot of silica or no silica? Is it highly viscous or not highly viscous? Where are we going to find these types of magma? And what kind of volcanoes those magmas form? Those are all going to be related, and I'm sure, I'm 100% sure that that's all going to be on the exam. Actually, hopefully they printed that out today. What else? Volcanoes. I would know the different hazards associated with each volcano type. So based on your volcano, you're going to have different lava flows, different pyroclastic flow, ashfall. What do volatiles do when you introduce it into a magma? What's the role of volatiles? Volatiles meaning gases and water vapor. Let's see. What else? For rivers and flooding, I would focus a lot on knowing the vocab there, what stage, what's discharge, how does stage relate to discharge, what's bank full flow, what's over bank flow, what do those mean, how to read a hydrograph, make sure you can read a hydrograph, know what the axes are, and know where flood stage is and where it isn't. Emma, are the quizzes helpful to study for the exam? I think they are. I would definitely look through the quizzes. You're not going to find the exact questions, but a lot of those questions on the quizzes and reading assessments are used as inspiration for the questions on the exam. So those would be great study materials too. Lecture slides will be great for you as well, and lecture recordings obviously as well. So those are all up on the YouTube channel and Canvas. I think I'm finally caught up with that, so they should all be up, and then this one will be up later today. So you should be good there. Is it still 50 questions, Samia? Yes, it is still 50 questions. Yeah, yep, just 50 questions. Equal amounts from each of the three sections that we went over. Any other lingering questions about anything? The meaning of life. How to make the best mac and cheese on planet Earth. Nothing, okay. All right, if you guys have any more questions and you guys over Zoom, email me, let me know. I'll be in my office most of the day today. I don't have office hours, but if you want to have an appointment, let me know. I have a couple appointments scheduled already. So I'll see you guys tomorrow. Yep.
Yeah.
Also, keep in mind, it's supposed to snow. If the university closes, we'll move our exam on Monday. Otherwise, plan on being here.
Thank you.
They said like 6 inches, and I don't think that's what's gonna happen. It's definitely not gonna happen. Yeah, so I don't think it'll, most of it's supposed to happen later in the afternoon too. So if anything, they'll probably close early, but sadly not closed enough to cancel the exam probably.